Welcome back to Software Engineering 2FA3 Discrete Mathematics with Applications 2. I am Bill Farmer, and we're going to start a new topic today entitled Turing Machines and Computability. Here's the outline for this topic. We're going to start by looking at the subject of computability theory. We're going to try to figure out what is computability theory all about. Then we're going to look at the great limitation theorems of logic, and that will be followed by an investigation of Turing machines, and finally we're going to look at undecidable decision problems. So what is computability theory? Computability theory, which is also called recursion theory, is the study of computable functions. So a function that's partial or total, that takes some set of arguments, is computable if there's an effective method for finding the output O, so finding the output O that's associated with a tuple of inputs. So a function is computable if there exists this effective method for computing the output from the inputs. Now there's some fundamental questions we would like to answer. The first is, what is an effective method? The second is, can every function be computed? And how do we show that a function is computable? And also, how do we show that a function is not computable? So we're going to address the first question first. So an effective method, which we could also call a mechanical method, but traditionally it's called an effective method, is a method for solving a family of problems in a mechanical way. And so an effective method satisfies the following requirements, which we'll go through one by one. The method consists of a series of steps in which each step results from executing a precise instruction. That's the first requirement. The second is each instruction is expressed by a finite number of symbols. The third is the number of possible instructions is finite. The method finishes after a finite number of steps. The method solves every problem in the family. And the method requires no ingenuity to succeed. So basically this is a finitistic method. It's finite in all aspects. It's fully precise. It's something that can be performed mechanically. And effective methods can be performed by machines as well as humans. And we would say an algorithm is an effective method for computing the outcome of a function from a given input. So let's go back to what is computability theory. There are two classes of functions that are particularly interesting to us in computability theory. The first is a set of functions f that take any number of arguments as input, which are natural numbers, and gives back a natural number as output. So this is an important set of functions that we will see again and again in computability theory. The other set of functions are functions that take some input and return either yes or no, or you can think of this as true or false, or 1 or 0. These functions represent decision problems. So a decision problem is a problem where you take an input and you have to make a decision, either come back with yes or no. And I is often the set of strings over an alphabet, sigma star. Now, a very important notion in computability theory is the model of computation. So a model of computation is a scheme for expressing a set of functions in some form that enables computation. So it provides a way of thinking about a set of functions so that we can compute them. And here's an example. DFAs is a model of computation for functions, and these are actually predicates because these functions return true or false or yes or no that represent membership in irregular languages. So DFAs are a model of computation, but they're a limited model of computation because they only allow predicates that represent regular languages. So a decision problem, which we've talked about before, is a problem to determine the answer to a yes or no question for a given input. And a good example is a given natural number prime. This is a decision problem. We can decide whether that natural number is prime or not prime. And a decision problem can be identified with a function from the inputs to yes or no, true or false, or 1 or 0. And many problems can be formulated as decision problems. So we're talking about a giant class of different kinds of problems. Now, a solution of a decision problem is a computable function that for each input returns as output a yes or no that correctly answers the question. And a decision problem is decidable if there exists a computable function that solves it. Now, Gottfried Leibniz, in the 1600s and very early 1700s, he postulated two things. These are two things he worked on pretty much his whole life. The first is the Characteristica Universalis. This is a universal language in which all scientific ideas could be expressed. And the other idea was a calculus rationator, a computer that could compute the truth or falsity of statements expressed in the Universalis, the Characteristica Universalis. So Leibniz had this idea that we could write scientific statements in the Characteristica Universalis, and then the calculus rationator would be able to tell us whether these are true or false. And Alonzo Church and Alan Turing showed independently in 1936 by construction that there are undecidable decision problems. So there's problems that we can express that are decision problems, but we cannot decide them. And this basically shows that Leibniz's grand decision problem, is a given scientific statement as true, this is undecidable. And examples of undecidable decision problems are the Entscheidungsproblem and the halting problem. And so Church, he showed in 1936 that this problem is undecidable, and Turing showed in 1936 that this problem is undecidable. And we're going to look at both of these problems in time. Now, I mentioned there are these models of computation. They are schemes for expressing sets of functions in a way that we can compute them. So one model of computation that we're going to look at very closely is the model of Turing machines. And we say a model of computation is Turing-complete is if it is equivalent to this model of Turing machines. This is a model that Church developed in around 1936. So a Turing-complete model is any model that's equivalent to the model of Turing machines. And it turns out that there's a whole bunch of models of computation that are Turing-complete. So all these models are equivalent. And I'll list some of the early important ones. Lambda calculus, developed by Alonzo Church. Turing machines, developed by Alan Turing. General recursive functions, developed by Kurt Gödel and Jacques Erbrand, and with the help of Stephen Kleene. Combinatory logic, which was developed by Moses Schoenfinkel and Haskell Curry. And post systems, developed by Emil Post. So these are all, you can see these are all developed roughly in the same decade or so. I've listed another kind of Turing-complete model of computation, unlimited register machines, developed by John Shepherdson and Howard Sturgis in 1963. So this model is especially good because it very closely mimics how actual computers work today. Now, all these models are computationally equivalent. They are all Turing-complete, and this is one of the most significant theorems in computing, that people were able to develop models of computation very different from each other, but they all capture the same notion of computation. They're all equivalent, and this same notion is what we call being Turing-complete. Now, Church and Turing developed a thesis that states that each Turing-complete model of computation fully captures our intuition of what a computable function is. So, no one has ever come up with an example of a way of computing that is not incorporated in a Turing-complete model of computation. These Turing-complete model of computations really do seem to capture exactly what we mean by a function being computable. But of course, this is not something we can prove. It could be, in theory, there's some kind of intuition that we have as humans for computation that is, no one has ever figured out, ever noticed that this is not incorporated in these Turing-complete models of computation. Now, the Church-Turing Thesis implies that every computable function can be expressed in any chosen Turing-complete model of computation. What this means is if you have a function and you have some effective method for computing it, then we will be able to represent that function in any Turing-complete model of computation. Now, the amazing thing is Church and Turing developed this thesis before there were modern computers. Okay, we're going to stop here, but next time we're going to talk about the great limitation theorems of logic.